Hello class, we're now going to learn about electromagnetism, about charges, the flow of electrons, opposite attracts and like charges repel. I think you might be shocked by how much you learn about electromagnetism in the next few slides. First, what do we mean when we say something is electrically charged? What is an electric charge? Well, here's some guidelines. Electric charges are monopoles. And we'll see what that means in a second. They're either positively charged, what we call like a proton, or negatively charged, like an electron. The person who first defined charges to be positive and negative was actually our own Benjamin Franklin. Prior to that time, scientists thought that electricity was like heat. It was a fluid that would flow. But we now know that electricity involves electrical charges, which are point charges, as shown in the next slide. So electric charges exist as monopoles. What does that mean? If you look to the left, you'll see a negative charge. If you look to the right, you see the red positive charge. Now, they're not really colored red and blue, but this is just so that you can distinguish between the two types of charges. From one charge, we see that we have arrows pointing in and the other pointing out. Now, this is arbitrary as to which direction they point, but the point is that these are opposite charges, and they are what are called point charges, or monopoles, and the field of this charge radiates outward or inward in a spherical way, that is, in all directions from the center of this point charge. That's sort of what we mean. And the influence of the charge dies off with distance, okay? Now, we've heard that opposite charges attract. What does that mean? Well, if you have a positive and negative charge that come close to each other, then there are these fields of attraction between the positive and negative charges. You see that's kind of represented by these arrows sort of going from the positive to the negative. Okay, that's good. That is an attractive interaction between the positive and the negative charge, between the opposite charges. You've also heard that like charges repel. What that means is illustrated in the bottom. If you have two negative charges, or it could be two positive charges, you'll notice that these sort of rays that are radiating in and out, they kind of shun each other in the middle region. And the result would be that these two charges would repel each other, would spread apart. Whereas in the top case, the two charges would be pulled together. Opposite charges attract, like charges repel. Now, the force of attraction between charges is given by the equation that is shown. Force of attraction is equal to some constant, we'll get back to it, times the product of the two charges, charge 1, which we represent as a Q1, the charge on particle 1, Q2, the charge on particle 2, the product of these charges divided by the separation distance between the charges. That separation distance being called r in this equation, so it's r squared. Again, the force of attraction, or repulsion, is equal to a constant times Q1 times Q2 divided by the separation distance squared. Now this constant K is called Coulomb's constant after Charles Augustin de Coulomb, a contemporary of Benjamin Franklin, whose research led to the equation above. Again, like charges repel, opposite charges attract, with a force of attraction or repulsion given by the equation above. Okay. Now let's compare for a second the strength of the electrical force given by the equation we just mentioned. Force equals a constant, Coulomb's constant, times the product of the charges divided by the separation squared. Let's compare that with the force of gravitational attraction, which we covered in a previous chapter. But notice that the equations are very, very similar in form. For a gravitational attraction, which is due to the attraction due to the mass of two or more bodies attracting each other, the force of attraction due to gravity is equal to the product of a constant, another constant, this time it's g, remember, times the product of the two masses, m1 times m2, divided by the separation distance squared. So again, notice the remarkable similarity of the two equations. You have a constant, it's either k or g, a product of, in the first case, the product of the charges, in the second case for gravity, a product of the masses. And in both cases, the force is inversely proportional to the distance squared, r squared, between either the charges or the two masses. Now, the one difference between electrical forces and gravitational forces is that electrical forces can be either attractive or repulsive. That is, like charges repel, opposite charges attract. Whereas with gravity, the force of attraction is only attractive. That is, two particles of mass m1 and m2 will attract each other. They do not repel each other. They only attract each other. Amazing similarity. Now, while gravity is what holds us on planet Earth, which keeps us from flying around and flying away from the planet, electrical forces actually dominate the behavior of matter around us. Okay, and I'll show you what I mean by that. Let's compare. Oh, I know, so many numbers and equations here, but we'll try to simplify it. Let's compare the gravitational and electrical forces. Let's consider a proton and electron, and we'll get to protons and electrons a little later in class. But you probably know they're really small, and a proton is positively charged and an electron is negatively charged. And they're so small that their separation distance, when they're close, their separation distance can be 10 to the minus 10th meters. That's the size of an atom. So the separation distance is not very large. So the question is, what is the force of attraction due to gravity between a proton and if we plug numbers into this equation for the gravitational attractive force, G times m1 times m2 divided by r squared, and we plug in all the numbers, don't worry about them, but if we plug in all these numbers, we get the force of attraction is 1.0 times 10 to the minus 47th newtons as the gravitational attraction between a proton and an electron. Now, first of all, that's a small number. Now, if we calculate the electrical attraction between a proton and electron using the equation shown, the force of electrical attraction is equal to this constant, Coulomb's constant, times the product of the two charges, Q1 and Q2, divided by r squared. And we plug in the corresponding constants in numbers for the charge on a proton and a charge on an electron and the separation distance, etc. We will get the force for an electrical attraction as 2.3 times 10 to the minus 18th newtons. Number, again, it's a small number, but now let me point out that for the gravitational force between a proton and an electron, that force of attraction due to gravity is extremely small. Look how many zeros we have. As compared to the electrical force between a proton and an electron, it's small, but it's much, much bigger than the gravitational attraction between a proton and an electron. The point is that while gravity holds us to planet Earth, when we talk about molecules, electrical forces dominate. Now we'll pause now and have a little quiz, and then when we come back, we'll talk about magnetism. So all of you with magnetic personalities, stay tuned.